In this video, we're going to do another proof of the Gauss summation formula, which I've written here. I guess I should quantify where the ends are coming from. And we're going to do a visual proof, or a graph theoretic proof, still using induction, but nevertheless a graph theoretic proof. And so let me just quickly say what a graph is, if you want to learn more about graphs. We have a graph theory course here. But a graph is just, it's a collection of, well, dots that we're going to call vertices, and lines connecting those dots called edges. So for example, that's a graph. We have 3 vertices and 2 edges. Another example is, maybe we're going to do a square. We have 4 vertices, 4 vertices here, each of the dots on the outside, and we have 2 edges. And there's a special type of graph called a complete graph. You pick the number of vertices, and I'm going to draw, scroll all the way down. I'm going to draw it for the first couple n. This is called Kn. K1 is the complete graph on one vertex. You just have the one vertex, and there's no edges that you need to connect to anything. And so that's it. K2 is you have 2 vertices, and you draw all possible edges. There's just one edge. K3 is you have 3 vertices, and you draw all possible edges. So there's 3 edges. K4, you draw 4 vertices, and then you connect all possible edges. So here there's actually 6 edges. And if you think about it for a moment, the number of edges in Kn is what? Well, how many edges do we need to draw? Well, of the n vertices, to specify an edge, we need to pick 2 of them. So what should it be? Well, of the n vertices, choose 2 of them to connect together with an edge. So that's n times n minus 1 over 2. In particular, this tells us that the number of edges in Kn plus 1 is n plus 1, choose 2, which might look familiar. It's that, if you use the n choose 2, the formula for the number choose 2. And that's exactly the right-hand side of the Gauss summation formula. So this is telling us maybe we can use some graph theory to prove this with induction. So let's keep this in mind. Actually, let's even highlight this just to indicate how important this is for the proof that we're going to do. So the number of edges in Kn plus 1, the complete graph on n plus 1 vertices, is n times n plus 1 over 2. All right. So let's see something interesting here. Let's look at K4 again. And I feel like I should be having more color here, but I think we can all deal. So I want to think about K4 as K3 plus 1. So suppose we're in an instance where we know that the Gauss summation formula holds for one of our n's. Namely, it holds, in this case, for n is equal to 3. Suppose we knew that. And this is one of the points of induction, is you suppose you know it for some n, and you then prove it for n plus 1. Okay, so suppose this is known. This is our hypothesis in the inductive step. And we can easily verify this. Now on the right-hand side, though, I want you to think about this as the number of edges in, well, both of these are that, but in particular, the right-hand side is the number of edges in K3 plus 1. Now, what happens if we add an edge? we add a vertex. So how do you go in particular from K4 to K5? So to go from K4 to K5, we will add a vertex and add how many new edges. So over here, maybe in gold, I'll put our new vertex. How many new edges are we going to have to add? Well, we're going to have to add 1, 2, 3, 4. Okay. So in other words, 1 plus 2 plus 3 represented the number of edges in K4. And then what we're going to do is we're going to add 4 more edges to get the number of edges in K5. And we already know, actually, since K5 is like K4 plus 1, another way of computing that is by doing 4 times 4 plus 1 over 2. Okay, so if we know already it holds for K4, by adding an edge, by adding a vertex to create K5, we just have to add in 4 edges. And so we see some inductive behavior happening here. So let's try to formalize that. So proof of the Gauss summation formula. We proceed by induction, or mathematical induction, or the principle of mathematical induction. For n equals 1, there's not really a lot going on there. N equals 1 is just 1 is 1 times 1 plus 1 over 2, which is true. We'll put our gold check mark. To really use the graph theoretic, I mean, you could use it here, but to really use it, it shows up at the inductive step. For the inductive step, the number, well, let's be really careful like we were before. We suppose that 1 plus 2 plus n is n times n plus 1 over 2, and prove 1 plus 2 plus n plus 1 is n plus 1 times n plus 1 plus 1 over 2, which we computed in the last video to be n plus 1 times n plus 2 over 2. Okay, so the same setup to the last proof, and scroll down just slightly. So what do we know? Well, we know that the right-hand side, let's write it like this, the number of edges in, let's see, this was not, this expression was not the number of edges in Kn. Let's go back up because I've forgotten what it is. It's the number of edges in Kn plus 1. Okay. Since the number of edges in Kn plus 1 is n times n plus 1 over 2, and we know that n times n plus 1 over 2 is equal to this expression, we also know that the number of edges in Kn plus 1 is this left-hand side. That represents the number of edges as well, because that formula holds. Okay, so by adding a vertex and connecting it to the original n plus 1 vertices, what do we get? Well, we add, let's see, we have to take that vertex and connect it to n plus 1 vertices. We have to add n plus 1 edges to our sum. Scroll down a bit more. So when we add a vertex and connect it to all the other n plus 1 vertices, we get that number. But this is also the number of edges in what? Well, we had n plus 1 vertices, and we added one more. So this is the number of edges in kn plus 2, which we have computed with our formula to be n plus 1 over times n plus 2 over 2 by our formula from before. You just replace the n with an n plus 2 instead of having an n plus 1 like we had. Thus, since they both count the number of edges in kn plus 2, they have to be equal. So 1 plus 2 plus n plus 1 is equal to n plus 1 times n plus 2 over 2. Let me scroll down quite a bit now. We've come to our conclusion. As both sides represent the number of edges in kn plus 2. This completes the inductive step. And completes the proof. Inductive, oops, got a little ahead of myself there. So there's a sort of a graph theoretic or visual proof of the Gauss summation formula, which also uses induction.